So let's do the root test real quick so that we can do a little review. Okay, so it's very, very, very similar to the ratio test, but so you have the series. So the series a sub n equals 1 to infinity. So if you take the nth root, so if, well, let's do, okay. So if the limit as n goes to infinity of the nth root of a sub n is equal to L is less than 1, then the series, take a wild guess. Converges, right? If the limit as n goes to infinity of, if the limit as n goes to infinity of the nth root of a sub n is equal to L, which is greater than 1, then the series diverges. And if the limit as n goes to infinity of the nth root of a sub n is equal to 1, what does that tell you? Yeah, the root test is inconclusive. So you have to do something else. Okay, so proof. Proof / fun times. Do you guys remember? No, this one's for the. This one is on the homework. Yay! Fun times. It's pretty similar to the one we did. Pretty similar to the ratio test. It's one of the book problems. Okay, so we have all the tests. I just gave you a handout of all the tests. So let's do. We'll write down a bunch and then we'll talk about different approaches and all kinds of examples and stuff. So let's do rapid fire examples and things. Let's see. So last time we did, all right, so how about series n equals 1 to infinity of 2n plus 1 to the n over n to the 2n. All right. So what do you think? So now we have all the tests, right? We have the so telescoping series, we have geometric series, we have the divergence test, we have the alternating series test, we have the ratio test, we have the root test, and we have the integral test. Okay, so what do you guys think about that? It looks pretty like there's a lot going on, right? A lot going on.
Can we use the root test to take out the n?
The root test is a good one to use whenever you have nth root and powers of n. So that sounds like a reasonable test. So let's try that. Let's see what happens. So to do the root test, we take the limit as n goes to infinity of the nth root of a sub n. So then we have 2n plus 1 to the n over n to the, well, it's n to the 2n, right? So how about if I rewrite it as n squared raised to the n? So what is that? Yeah, this is just 2n plus 1 over n squared, right? So this is the limit as n goes to infinity. So the n's cancel out the root, right? So then you have 2n plus 1 over n squared, and what is that equal to? 0. So what does that say?
It's convergence.
converges. Yeah. And actually, it not only converges, it converges absolutely. Okay, so, all right.
So can you only do this when n is starting at 1?
Well, I mean, yeah, well, you take the limit as n goes to infinity, so it doesn't really matter if the series itself starts at 0, because you don't have to like actually plug in the number 0. Like, you're not finding the 0th root or anything like that. You know, if you were to plug in 0, it would be you would be plugging it into the series itself. So as long as it's defined, then you're okay. So there's no restriction there. Yeah.
So if n was 0 and let's say everything was n to n negative 3, I could move that 3 to the n. I can go backwards. I could, instead of n0 it would be n3, n equals 3, and then I can make it n. Because I know you can move stuff from the n underneath the summation back and forth.
Yeah, this particular series, you can't start at 0, but it has nothing to do with the root test. Why can it? Yeah, it's not defined, right? At n equals 0, you plug it in and it doesn't exist. So that's why this one doesn't start at 0. But it doesn't mean that you can't have a series that starts at 0. So like, it doesn't have to start at 1 to be able to use the root test. Okay. All right. Next. Let's see here. Got a lot of stuff. So this is, from everywhere. It's not just the root test. So let's do n equals 1 to infinity of 2 to the n factorial over n plus 2 factorial. All right.
Factorials, that's going to be it. Yes.
So when you have factorials, usually you want to use the ratio test. But there's something else that you might notice with this one before you even do that. What is it? Before you even do anything? You can simplify the factorials, right? Because you have a factorial on top, you have a factorial on bottom. This n plus 2 factorial, that's n plus 2 times n plus 1, right? Times n factorial, right? Because this is n plus 2 times n plus 1 times n minus 1, n minus, and so on and so forth. So anytime you have, factorials on the numerator and the denominator, if they can meet somewhere, then you can write out the beginning part of 1, and then until you get to, in this case, we get to n. So then this one is going to cancel out with that one on top, right? Does that make sense? So then this series is actually, this is just the sum from n equals 1 to infinity of 2 to the n over n plus 2 times n plus 1. And this actually, what do you notice? Do you even have to do the ratio test?
Oh, you can move the 1 to the n. So 2 to the n plus 1 or minus 1.
No, I mean you can, but not. That's not necessary. What do you? No, something simple. Yeah. What happens if you take the limit of this, just the sequence itself? If you take the limit as n goes to infinity of 2 to the n over, let's write this out. This is n squared plus 3n plus 2, right? What is that? Infinity over infinity, right? But if you do L'Hopital's rule, what happens after a couple times? Yeah, the bottom is going to go away, right? And the top is going to be there. So you do L'Hopital's rule twice, and you see that this is actually going towards infinity, right? So what does that mean? Yeah. Diverges. So if you did the ratio test, you might have seen that it also diverges. In that case, it would have been, what should happen if you do the ratio test? If it's going to work, you should get that it's greater than 1, right? Should we try it just for fun? Or? Okay. Yeah? Just to try, just for practice? The ratio test? So if we do the ratio, okay, so we already know it diverges. But we go, okay, let's try the ratio test anyways. To confirm. So we'll take the limit as n goes to infinity of a sub n plus 1 over a sub n, right? Okay, so a sub n plus 1 is going to be 2 to the n plus 1 over n plus 3 times n plus 2, right? Where do those come from? It's from plugging in n plus 1 into the denominator, right? Okay. So then, and then divided by a sub n, right? So I'll do times n plus 2 times n plus 1 over 2 to the n. So what happens with these 2's to the n's?
You can separate 2 to the 1 times 2 to the n and
Okay, so I get rid of this and I just have a 1, 2 left over, right? Cancels out with that one. So then what I'm left with is, so what are the dominant terms in the numerator? I have an n squared, but it's actually a 2n squared, right? Right, so this turns, so all of this, so the dominant term in the numerator is a 2n squared. And the dominant term in the denominator is going to be a just n squared, right? So if you take the limit of that, just by looking at the dominant terms, this is going to equal to 2, which is greater than 1. So by the ratio test, it diverges, right? Questions? Okay. All right, let's see. We're plowing through here. How about we do this? I'll give you guys I'll write down a couple for you guys to try on your own. Okay, so try that one, and then how about tangent of 1 over a. All right, so for this first one, what are some of the options that you guys came up with?
Limit comparison test.
Okay, so limit. So these are, we'll write down our possibilities. So I don't know if you guys want to write this down. This is just us like brainstorming. So limit comparison test, but what would you use for the limit comparison test?
1 over n cubed.
Natural log of n over n squared.
Well, there are a couple of issues. So you don't really want to do 1 over n cubed because the n cubed is similar to the n plus 1 cubed. But the 1 isn't very similar to n times ln of n. But ln of n is kind of close to which function?
Square root.
Yeah, square root of x, right? So it's kind of similar to that. So you can kind of, if you think of natural log of n being close to root n, then you might think of comparing with n times root n over n cubed. And this one, this is n to the 3/2 over n cubed, which is 1 over n to the 3/2, right? So if you're going to use this one to compare it with, then what does your gut instinct tell you? That it converges, right? Because 3/2 is greater than 1. So then the issue is would it be easier to use the comparison test or the limit comparison test? So the comparison test is better to use if the inequalities are easy to show, right? So like if you can show, if it's easy to show, so this is the question. So we're testing for convergence, right? So that means that what the inequality that we would want is that n ln of n over n plus 1 cubed, we want that to be less than or equal to n root n over n cubed, right? Which it depends if that's easy to show, right? So the denominator, is that in the right? That one is, right?
Yeah.
And then, so then the issue is so like this, the denominator part is okay, right? Because n plus 1 cubed is obviously greater than n cubed, so that means 1 over n plus 1 cubed is less than 1 over n cubed, right? So that part's okay. So then what we need, so the n's are the same, right? So then what we really need to know is, okay, well, is ln of n less than square root of n? For all n greater than or equal to 1, right? So if we can show that, then we're good to go, right? And so there are a couple of ways to show this. So this is a good one to sort of keep in the toolbox. But let's take a look at, it's worth going through. So if I take a look at the graphs of these, so ln, so let's say starting at 1, so this is 1 right here. If I draw, let's say ln of n, ln comes up like this, right? And then it goes like that. And square root of x starts, let's say I do this, and so it starts here at 0, right? And then it kind of goes up like that. But then the question is, does the natural log function ever go above the above square root of x? Okay. Well, you can say no, but how can you show that it?
Can we equal them and see if they ever cross each other?
You can do that, sure. So there are, okay, so here are a couple of options. So we know that at 1, so it's obvious that ln of 1 is less than square root of 1, right? Because ln of 1 is 0 and square root of 1 is 1. Okay, so that's obvious. But then, so there are two things. You can either set them equal to each other and see if they intersect, right? Or, so if you can show that they don't intersect, then you're good. Or you can compare the rates of change of both for values of x greater than 1, right? So if you look at the derivative and you can see that the rate of change of the root is greater than the ln, well then they're never going to cross, right? Because this one's increasing faster. Does that make sense? Yeah? You guys with me, or you guys did? Okay, all right. So Well, since we're on this exploratory path to great discoveries, why don't we do both? Huh? Yeah, okay. All right, so then over here we'll ask ourselves, hey, does ln of x equal to square root of x? So for all values for after 1, right? So if I'm going to try to solve this, what would I do? What is this the same as?
Raise it both to e. Or square root.
Yeah, so does e to the x equal to, or sorry, not e to the x, e to the, well, let's do it the other way. Let me keep them the same. So does x equal to e to the root x at some point? That's what that says, right? What would you guys say? Why not? I mean, it's definitely no, but is it obvious or, I mean,
This is like gives sense.
what is it?
This is like I can't say anything else.
Well, if you compare the two, so this is the exponential function, right? And then you have just
If you
y
square
equals to
both,
x.
Could you square both sides and then
Um,
at what point is 2x?
well, but yeah, that wouldn't help. I mean, the problem is the type of functions that you have, right? Solving that is not exactly the best way. So, well, you could again compare the rates of change of the two, right? But why don't we just, okay, so, without having too many tools in our arsenal, then let's compare the rates of change. So the derivative, so we want to compare the derivative of natural log of x and the derivative of square root of x. So what's the derivative of ln of x? So this is 1 over x, and the derivative of root x is 1 over 2 root x. Okay. So what for x values of x greater than 1, what do you notice about the rates of change? Which one is bigger?
One of, it would be on the right hand side.
Yeah, 1 over 2 root x is greater than 1 over x, right? So what this tells me, whoops, drew it the wrong way. What this tells me is that that square root of x is increasing at a faster rate than ln of x for all values of x greater than 1, right? So if the question is, do they ever intersect? Well, obviously they are not, because what I've just shown is that this one is increasing at a faster rate than this one is. So then it's never going to, they're never going to touch, right? Does that make sense? Yeah.
X is 4. Aren't they the same or something? The rates.
If x is 4, right, the rate is the when x is 4, these are the same. When x is so this is, I mean, I guess, well,
still okay, just because it's the same slope at one point doesn't mean, if you continue out on that path.
Well, yeah, but you have the rate of change is, so this is true after x equals to 4, right?
Yeah, because then at 9, if x is 9, the right hand side is 6.
So for x greater than or equal to 4,
Yeah, because then,
yeah, but they still don't intersect before then, right? So anyways, that was kind of a bit of a tangent that we went off on. But the whole point of that was that this inequality holds, right? So then that means that this series is going to what? Converges, right? By the comparison test? Yeah?
I did it a different way. I got it.
Yeah, I don't know. Did any of you guys do the limit comparison test? Probably, it would have less.
So does it tell us where it converges to?
You can. You can't. It's very difficult to find explicitly what it converges to. You can estimate it, right? So like if you add up. If you add up 1,000,000 terms, then that would be a pretty good estimate. And you can estimate how far off you are, which we haven't done.
Oh
But anyways, yeah. So yeah, you can approximate what it converges to, but you can't. It's not very easy to find what it converges to. Anyways, all right. What about this one? Did anybody do this one? Raise your hand if you got this. Anybody?
I got 0.
You got 0.
It came in. Like if you just do the limit of that, it's 0. So that's inconclusive, and then you have to.
So yeah, you got to keep going. So any ideas on something we can try? Let's see. Well, it's definitely not geometric, right? Not alternating. Would the ratio test be a good option for something like this? Doesn't really look like something that would benefit from the ratio test, right?
I think we have to compare it.
Maybe the comparison test, or what else? What other test? Maybe the integral test. So okay, so let's see. So possibilities.
Oh, absolute magnitude.
So maybe the integral test, and maybe the comparison or limit comparison test. Any other one that we should maybe try? No? All right, so which one do you guys want to try first?
Integral test.
So if we draw, maybe we should, maybe a little mini picture would help. So this is tangent of 1 over n, and n is going to infinity, right? So it starts off, what is the argument of tangent start off as? The first value is
Tangent of 1.
1, which is around, so at pi over 4, tangent's equal to 1, right? And pi over 4, that's a little bit less than 1, right? So, 1 is, I don't know, let's say right here. All right, so something like that, right? And so tangent looks like, I don't know, something like that, right? So the part that I'm looking at is something like that, right? Ish, right? That little section. So what I'm looking at is, so right here, so the first value of the first term of the series is right here, tangent of 1, and then all of the terms of the series are going towards 0, right? So, interesting. So what do you guys think there? Are they positive?
Yeah.
All positive. Are the values decreasing?
No. Wait.
Yeah, they are decreasing, right? As n goes to infinity, all the values of the sequence are decreasing, right? So should we try the integral test? Because that's what you need, right? They have to be positive, decreasing, going towards 0, obviously. Should we try? Maybe?
Yeah.
Does that look
Change
like...
our tangent up a little bit.
Well, we have to be able to integrate it, right? So we go, okay, well, let's try integral. So the integral from 1 to infinity of tangent of 1 over x dx. All right. So how do we integrate that?
Or natural law?
Natural log of secant. Yeah, natural log of secant plus tangent.
No.
Just secant.
Just secant.
Secant squared.
No.
Yeah, ln secant.
But that's just tangent. This is tangent of 1 over x. If it was just tangent, well then yeah. But this is tangent of 1 over x.
Oh, we gotta use no.
So hypothetically, if we were to do u equals 1 over x squared, then du is... This doesn't look like it's going to end well, does it? No, right? So we have du is going to be negative 2 over x cubed dx. So dx is negative 2x cubed. So you have... and so that doesn't... okay, so here it wasn't the conditions that it's positive and decreasing that fail us. It's our ability to integrate this doesn't seem to be a very good idea. So we scratch that off the list and we go, okay, well let's go back to the drawing board. So the comparison test looks like a good option. What can we compare it to though? And you might get a good idea from the picture.
Can we compare it to
Well,
like
like pi over 4 over n.
So if you take a look at tangent just in that little piece, that little chunk, that pink chunk, what do you notice?
like x squared?
What does it look like the most? Kind of looks like just a line, right? Y equals x. So in this little chunk, if you look at it, I don't know if this is going to work, but I'm just saying. So in this little piece right here, just in that little piece, don't you agree that tangent of x is approximately equal to the line y equals to x? right? Because this is 1 and there's 1, and so it's kind of close, right? So then you can say, okay, well then that means that maybe tangent of tangent of 1 over x is approximately 1 over x. So that maybe gives you an idea that if you compare it with 1 over x or 1 over n, right, that it might work. So then you hope. There's a lot of hoping, praying if you're of that what's the word I'm looking?
Spirituality.
Yeah, sure. Yeah. So now, out of the two comparison tests, which one is the best option for us for this particular function? Limit comparison or straight up comparison? Would it be easy to show that is either less than or greater than, or do we even have an idea of what
Straight
is?
up comparison. Right.
But if you're going to use the comparison test, you have to be able to show the inequality. So you have to be able to show that tangent of 1 over x is either greater or less than 1 over x, depending on what you're trying to show, right? And is that easy to show?
And greater.
No, right? Because tangent, no. Okay, so we're going to use the limit comparison test. Okay, so let's see. All right, so after all of our scribbles, we've decided limit comparison test with 1 over n. And if this doesn't work, who knows? I don't know. We go home. All right, so the limit as n goes to infinity of tangent of 1 over n over 1 over n. So what do we do here? What is this equal to? This is 0 over 0, right? So we can use L'Hopital's rule. I'm hoping this works because I'm at this right now out of ideas. So this is the limit as n goes to infinity of the derivative of tangent of 1 over n, which is
Secant squared 1 over n times
secant squared 1 over n times
negative 1 over n squared.
negative 1 over n squared. Okay, over 1 over n. So the derivative of 1 over n is negative 1 over n squared, right? Okay, so all right, adios amigos. And then I have the limit as n goes to infinity of secant squared of 1 over n. What is that? So secant is
Divergence. Doesn't it go up? Oh, it's the limit of
but what is secant? Secant is 1 over cosine, right? Okay. So I have 1 over cosine. The 1 over n is going to 0, right? So this is going towards 0. So 1 over cosine of 0 is 1, right? Yeah. Cosine of 0 is 1. So 1 squared is 1. So this is equal to 1. What does that mean?
Oh, convergence. Maybe. Wait.
What does the limit comparison say? Okay, so if the limit is equal to a number, if it exists, basically, right? Then they either both converge.
So you have
Both.
to do the limit of b. So you have to do the limit of 1 over n.
But we already know, right? What do we know about the series 1 over n?
Oh, it's a p integral t equals 1.
Yeah.
So it's back
yeah, it's the diverge, right? So the series diverges.
So if you had
Those are the harmonics, I'm sorry.
Yeah.
yeah, like sine, if we start with sine of 1 over n, we wouldn't be able to solve it.
Well, sine would be different. I don't know. Sine of 1 over n. Well, kind of looks the same, at least for between 0 and 1. If you would have done it,
Oh, so you,
yeah, it would have come out to be the same actually, right? Because you would have gotten cosine.
So what did we have to do after we got 1? We're supposed to be what?
Well, remember, so if this is greater than 0,
Yeah.
so 1 is greater than 0, then that means that they either both converge or both diverge. So it diverges by the limit comparison test since this series, 1 over n, diverges. So we compared it to a divergent series. And so that's it. Good times, huh? Those were good ones. We were lucky that it worked because I wasn't sure. We ran out of options there. Okay. You guys want to take a little break?